Alrighty, folks. Hello and welcome back to Math 38 or 3108. This is Abstract Algebra 2, lesson number 2. So in lesson number 1, we were talking about arithmetic in Z. And the three main topics we were dealing with was the first one, the division algorithm. So the division algorithm is where I take an integer and I could break it apart into a product and a sum, that sum being the remainder. Now, specifically when that remainder was equal to 0, so I can take an integer and break it into just a product of two things, what we were talking about was then divisibility. And we went through a number of different conditions that we had for divisibility. And then the last thing that we talked about was prime numbers and how we could take an integer and we could break it down into a product of primes. So long as that integer is not 0 or plus or minus 1, we could break it down into a product of primes, and to some degree that it was a unique decomposition or unique factorization that we can do. So more or less improving on that idea, or not improving, but extending on that idea. In this lesson, the basic concepts of integer arithmetic are extended to include the idea of congruence modulo n. So I did talk about this very, very briefly in the last set of lessons, but we never properly defined it. I said I would do that. I'm going to do that here. So congruence is going to lead to the construction of the set Z sub n of all congruence classes of integers modulo n. And this construction will serve as a model for many similar constructions that we're going to see throughout this course. So again, this is building upon the foundations of what we are going to use for the remainder of the course. So let's jump into this. So starting off with our first definition. Let a, b, and n be integers with the only condition is that n has to be strictly greater than 0. Then a is congruent to b modulo n, and we write that as a, and we're not necessarily saying equal here, we're saying it's congruent. It's going to have the same sort of flavor, but it's not exactly the same. So to indicate it's not equal, we do the 3 lines here. So a is congruent to b modulo n, and this is true provided that n has to divide a minus b. So basically what we're saying is if the distance between a and b is in fact a multiple of n. So to see this, let's jump to the workspace for a second. And let's say I did a number line here for the integers. We'll start at -6, -5, all the way up to 0. And we'll go 0 up to, we'll say 8. And of course, this extends all the way up to positive infinity, all the way up to negative infinity. So the general idea of what we're doing is we are going to partition off the set of integers. So we're going to break it down into partitions. These partitions are going to be of size n. So let's say we're doing mod 3. So my first partition, my main partition, is going to start at 0, so it's going to include 0, and then it's going to include 3 elements. So 3 elements to the right. So I have 0, 1, and 2. So this makes up my first main partition. And then again, continuing on at 3, 4, 5, I have a second partition. 6, 7, 8 is another one, and so on and so forth. Now that's moving from 0 to the right. I can also do this from the left. So -1, -2, -3, -4, -5, -6, and so on and so forth. So you'll see we're able to break apart Z or partition Z into distinct partitions of size 3. By distinct, that there is no overlap between them. Now the general idea is the elements inside of each partition, if we index them, so each one at, say, position I is going to behave in exactly the same way. So what do I mean by that? Well, let's look at 1 here. So this would be in the second position. If 0 was the first, 1 second, 2 is the third. So if I grab the 1 position for every partition, basically what we're going to be saying is they're all going to behave in exactly the same sort of way. So how it behaves in the main partition here is going to be exactly the same as how it behaves in the second partition here, and over here, and over here, and over here. So basically, they are the same, they just look different, and the distance between each of them is a multiple of n, or in this case, it's a multiple of 3. So if we go in between 5 and -2, well, that's a distance of 3. If we're going -2 to 1, well, this is kind of a funky looking color here. I thought that was just going to be a purple, but it's not. Interesting. -2 to 1, distance of 3. 1 to 4, distance of 3. 4 to 7, distance of 3. So each one of these consecutive ones are congruent modulo n, but also it doesn't have to be consecutive ones. I can look at -5 and 1. So -5 to 1 is not a distance of 3, but a multiple of 3, because I have 3 units here, I have 3 units here. So again, it's 2 times 3. But that's the whole idea, is that the distance between each one of these points is the same by a multiple. So the general idea here is that really we don't need to focus on all of Z. We just need to focus on, when we're dealing with congruence modulo n, we just need to focus on the main partition here. So again, if the distance between A and B is a multiple of n, we say that they are in fact congruent. All right, so let's jump into our first theorem. So our first theorem states that let n be positive, or it's a positive integer. So for all a, b, c inside of Z, we have the following 3. So we say A is congruent to A mod n. Well, that makes perfect sense because the distance between A and itself is nothing. And that is a multiple of n because I can multiply n by 0 and I've gone nowhere. If A is congruent to B mod n, and B is congruent, or then B is congruent to A mod n, which again makes sense because if I'm looking at this from my whiteboard here, if I'm looking specifically at, say, 1 and 4, well, I can say 1 is 3 units to the right to get to 4, or 4 is 3 units to the left to get to 1. It doesn't really matter which direction I'm going to. It's still the same amount of units on either side away. And of course, last but not least, if A is congruent to B mod n and B is congruent to C mod n, then what has to be true is A is also congruent to C mod n. And again, very easy to see from the board space here. If I look at 5, 2, and say, or -5 here to -2 and 1, well, I can say -5 is congruent to -2 mod 3, and -2 is congruent to 1 mod 3. But that also means, because again, they're all in the same ith position in their respective partition, that 5 and 1 also mean exactly the same thing, or will behave in exactly the same sort of way. Because again, it's just another multiple away from where we need to be. So a little note here, let n be a natural number. Congruence modulo n forms equivalence relations on Z in itself. So if you've done 2108, you know what equivalence relations are, which just needs to hold the 3 properties of they need to be reflexive, symmetric, and transitive. We're not going to be covering it because, again, it's assumed that you would have covered it in 2108. If you haven't taken 2108, just do a quick Google search. You'll be able to find what it is. Oops. There we go. So let's jump back over to the board here. And because this is a relatively straightforward one, and we do want to prove at least something from each section, let's prove a couple of these because some of them are fairly straightforward to go through. So we'll take the first one. So this is what we want to show. A is equivalent to A mod n. Now this is true if n divides A minus A. So we need to show that this is in fact true. So note, A minus A is equal to 0. And what is always true is that n divides 0, because we could write 0 as n times, well, whatever. It doesn't really matter because, it does matter. Oops. There we go. Well, that's a horrible looking 0. Let's try one more time here. There we go. n times 0 is equal to 0. So this holds true. Therefore, if this is true here, n divides 0, and we can write 0 as a minus a, then n divides a minus a, which implies a is equivalent to a mod n. There we go. We could do the same thing, or relatively the same idea, for 2. So we are given that a is equivalent to b mod n. So if this is true, then n has to divide a minus b, which means that a minus b is equal to n times some k. All right, so let's just multiply both sides by -1. So negative a minus b is equal to n times negative k. I could write my left-hand side as b minus a is equivalent to, or is equal to n sub k, which means that n divides b minus a, which means that b is equivalent to a mod n. All right, the last one we'll leave as an exercise for you folks to play around with. All right, so another theorem that we have is that if a is equivalent to b mod n and c is equivalent to d mod n, then we have the following true. If I take a and add it to c, this is the same thing as b adding it to d mod n. So jumping back to my whiteboard here, bringing back down what we had before here, the number line. So let's look at this as a and b is 1 and 4, and we'll do 2 and 5 would be kind of like c and d here. So if I take 1 and 2 and I add them together, that's going to get me 3. And if I take 4 and 5, add them together, well, that's going to get me 9. So what does it get me? It gets me the first position here. It gets me the first position here. Again, behaving in exactly the same sort of way. And that's what we would expect to see overall. And same idea for multiplication, just using the graphical representation of this. Now, of course, we could prove all these. Not going to prove it all, but we can see from the picture that, again, it's going to behave in the same way. That if I take a, multiply it by c, this is the same thing as b and d. So, and again, I'm talking the same in the fact that it's going to be behaving in the same way. All right, so several essential arithmetic and algebraic manipulations depend on these facts under equality. But what we're going to do now is we are going to show that the same thing is true for congruence. So the whole idea is we are relating these two things, equality that we did in Z and equivalence of what we're going to do in Z mod n. They're fundamentally different, but very, very close to the same sort of general idea. All right, so for this definition here, let a and n be integers with n greater than 0. So the congruence class of a modulo n, and we refer to this as, or we define this as using the notation here, in square brackets we just have a, is the set of all those integers that are congruent to a mod n. So what do I mean by that? I mean a is a set, and that set's going to contain all the b's, where b is an integer, such that b is equivalent to a mod n. So again, when we're talking about equivalence, again, we're talking about all those things that are of a certain distance away or a multiple of that distance away. So we can really rewrite this as b, it's the set of all b, where b can be written as a plus nk, where k is some element inside of z. So it's easy to see what numbers are equal to a given number in z, which would just be a. So if I had 5, well, the only thing equal to 5 in the integers is in fact 5. But again, this is different, and I'm really stressing this part. This is different when we're talking about congruence, because with congruence classes specifically here, we're dealing with sets of numbers, not a single number in itself. Now, in terms of what we have here, this is the presentation I tend to prefer because it's useful in practical computation, but it also looks very familiar to us, where the general idea of this here is the division algorithm. So if I have B and I have my divisor, which my divisor in this case is going to be n, if I divide B by n, well then I'm going to have some integer k where I'm going to have a product, and a is going to be my remainder. So the idea of this, in thinking of the division algorithm, the congruence class of A is the set of all B such that when we divide it by n, the remainder is in fact A. So using this idea, let's jump into this last exercise here, and this is going to complete the first part of the video. So for example 1, we want to consider what happens when we partition Z by congruence mod 2. Let's bring all this up here. So this is example 1 or exercise 1. All right, so we're doing this congruence mod 2. So just from the definition that we had on the previous slide, so the congruence class of A, we can define this as the set of all B where B is equal to, and I'm going to write this slightly different. This is going to be nk plus A. So I just reorder this where the multiplication is first, the addition is the second. So looking like the division algorithm. Given k in Z. There we go. So basically the whole idea of this is if B is an element of Z, and we're going to say n in this case is equal to 2, then by the division algorithm, if I take any integer inside of Z and I divide it by 2, what is it going to look like? Well, it's going to look as follows. B is going to be equal to some n times 2, or actually I should do 2 times k, look a little bit nicer. 2 times k plus A. So A is going to be the remainder, but we know the remainder of these ones is greater than or equal to 0. Whoops. Greater than or equal to 0, and strictly less than what I'm dividing by the divisor, which in this case is 2. So really, A can only be 0 and 1. So if, we'll go through the only two cases, if A is equal to 0, then what do these look like? Well, this is all B that are equal to 2k. So my congruence class of 0 is going to be made up of all even integers. Because for any k, I multiply that by 2, and k is an element of Z. That's all of my even integers inside of Z. Now if, on the other hand, A is equal to 1, what does B look like? B is equal to 2k plus 1, which we know happens to be all the odd integers. So my congruence class of 1 is equal to all odd integers. So if I have all even integers, all odd integers, basically these two congruence classes break apart or partition off all of Z. So that's exactly what it looks like. So this is the end of example 1. We'll see you in the next videos.